All right, today's lesson is on Boxplots, Outliers, and Resistance. So starting off, imagine a boss is recruiting you to work at their company. They tell you typical salary at our company is more than $65,000 per year. Sounds pretty good to start out. The devil's in the details, though, and sometimes recruitment statements like this might not reflect the full reality. So that brings us to today's key question. When you hear a statement like this, how can you use the tools of statistics to figure out how much money you might really make? So with that in mind, moving into our guided notes. So starting off, got 4 topics, starting with 5-number summary and changing units. So we'll start with a very simple data set that has 2 values, 1 and 3. If you find the average of this data set by adding them together, dividing by 2, you get a mean of 2. When you find the range by subtracting 1 from 3, you also get a value of 2. This means that the maximum value of my data set 3 is 2 units above the minimum value of 1. Now, let's imagine that we add 3 units to each data value in our set. If we add 3 units to the 1, it becomes 4, and then the 3 would become 6. Whereas the mean of our original data set was 2, now the mean is 5. So just like each data value, the mean also increased by 3 values. Recall the range was also 2, or was 2 at the beginning. We can see that the range of our transformed data is also 2. So note, the range did not change after that transformation. So the mean changed, the range did not. This reflects a general point. If you add or subtract every data value by a constant, they all shift by that exact same amount. This means that measures of center will also shift with it. But measures of spread will not change because these values all shift by the consistent amount, so the spread doesn't change. It doesn't become more or less spread out, they just got shifted. So now imagine we multiply each data value by 2. So if you multiply 1 by 2, you get 2. 3 by 2, you get 6. So now we have 2 and 6. So if we find our mean of our new data set, mean of 2 and 6 is 4. So just like the data values, the value of the mean was multiplied by 2. If we look at the range, right, the original range was 2. The range of the new set is 4. So the range was also multiplied by a factor of 2. So unlike addition and subtraction, both multiplication and division change the values of larger and smaller numbers in different ways. Specifically, when you multiply by a larger number, or multiply a larger number by a constant, its value shifts by more units than when the smaller number is multiplied. And it works the same way with division. Therefore, when you multiply or divide data sets by a constant, both the center and spread change. Generally, the measures of center and spread will each scale the same, multiplying or dividing factor. In our case, multiplying by 2 shifts the values up, increasing the mean. The multiplication also increased our maximum by more units than our minimum, so the spread between them also increased. Now, let's look at these principles when applied to the main data set for this lesson, salaries of the company. So it's a small company with 13 employees. Each of their salaries in thousands is listed here. All right, just note, so 38 means 38,000, and 164,000 is the 164. It's probably the boss. These values also happen to represent the minimum, median, and maximum. So you've got the minimum of 38, the median of 55, and the maximum of 164. Okay, we can then find our quartiles, or the mini medians, of the lower and upper halves. We get 46,000 for Q1 and 76,000 for Q3. So now I have 5 numbers there. Okay, there's a term for that. It's called the 5-number summary. All right, the minimum, the quartile 1, the median, quartile 3, and the maximum. All right, so those are known as the 5-number summary. They divide the data into quartered segments and provide an overall sense of the scale and variation in the values. So basically, there's quartered segments, so within each section is 25% of their data. So now let's see how different transformations of this data set affects the 5-number summary. So imagine a company had a good year, every person gets a $5,000 raise. How would the summary statistics change? To figure this out, since the data set is already on the scale of thousands of dollars, we can go ahead and add 5 to each value. When we do that, here are new values, each increased by 5. Here's the new 5-number summary. Let's break it down. So the 5-number summary values in the original data set are here. After the $5,000 raise, as you can see, just as every value in our data set increased by 5, so did every value in the 5-number summary. they also shifted upward by 5. In addition to the 5-number summary, we can also look at various measures of center and spread, which we can see below. Just like each part of the 5-number summary, the new mean was 5 units higher than the original mean. So we can see that our two measures of center, the mean, median, and mean, both shifted up with the rest of the data set. However, the measures of spread, the standard deviation, the range, the IQR, and variance all stayed the same. This follows from the demonstration of the simpler data set we saw earlier. If you shift each data value by the same amount, by either adding or subtracting by a constant, the measures of center will shift with it. The spread between those values doesn't change. So now, going back to the original salaries before the raise, look at a different potential transformation. So imagine we've got a Canadian worker thinking about Jordan and Company. To compare pay at their current job, which pays in Canadian dollars, they want to convert the new company's US dollar salaries into Canadian dollar amounts. At the time, the exchange rate was that $1 US was equivalent to the value of 1.3 Canadian dollars. So to convert these salaries into their Canadian dollar equivalents, all we have to do is multiply them by 1.3. Once we do this, we get the following salaries now in Canadian dollars. And if we find the new 5-number summary, we get the following. All right, now let's compare the new 5-number summary to the original 5-number summary when the salaries were given in US dollars. As you can see, just like how every data value was multiplied by 1.3, so are the values of the 5-number summary. Then when we look at the remaining measures of center and spread, we see that it's the same thing. So just like when we multiplied the very simple data set at the beginning of the lesson by 2, and everything scaled up by 2, we multiply by 1.3, the measures of center and spread all scaled by 1.3 as well. However, there is one exception, variance. As a reminder, the variance is a square of the standard deviation. Like the rest of the measures, the standard deviation scaled up by a factor of 1.3. However, if we calculate the original variance and the transform variance by squaring standard deviations, we get the following values. It turns out the variance is 1.69 times the variance in US dollars, which departs from the 1.3 factor we saw from the other measures. Where does this 1.69 number come from? Well, it's just 1.3 squared. Because variance is given in square units, when you scale all the data values by a constant through multiplication or division, the variance will scale by that square of that constant. All right, now moving on to outliers. Turning back to our original salaries, we saw that maximum salary of $164,000, that boss's salary. It's unusual, but is it unusually high enough compared to the rest of the salaries, and is it considered an outlier? So to determine if a data value is an outlier, we need to calculate what's called outlier boundaries. Any data value that falls below a lower outlier boundary are considered outliers, as are any data values that fall above a high outlier boundary. There's two methods for calculating outlier boundaries. The first method is called the interquartile range method. In this method, the lower bound is a distance of 1.5 times the IQR below the first quartile, and the upper bound or boundary is a distance of 1.5 times the IQR above the third quartile. Let's look at how this works. So the first and third quartiles were 46,000 and 76,000. IQR is the difference between these values, Q3 minus Q1. So we take the values and subtract them and get an IQR of 30,000 or 30. So now we have all the ingredients we need to use the formulas for outlier boundaries. I can plug in Q1 and the IQR to the formulas for the lower bound, and we get a lower bound value of 1 or 1,000. As you can see, there are no salaries below 1,000 per year, so there are no low outliers in this data set. Now we turn our attention to the upper bound. We plug in Q3 and the IQR, so Q3 was 76, IQR is still 30. We get an upper bound of 121 or 121,000. As you can see, we do have a salary that's higher than the upper bound, the boss's salary of 164,000. So by this method, we can in fact consider the boss's salary as an outlier. It's so unusually high that it goes above our upper bound and is considered an outlier compared to the rest of the company. Now, the second method for determining boundaries for outliers is the standard deviation method. In this method, the lower bound is 2 standard deviations below the mean. The upper bound is 2 standard deviations above the mean. For our salaries data, the mean is about 65.5 or 65,500. Standard deviation is about 34.2 or 34,200. We can plug these ingredients into our boundary formulas. For the lower bound, we plug in the mean and standard deviation, and we get a lower bound of negative 2.9 or negative 2,900. As we would hope, the company isn't taking away money from their employees. So no salaries below that, so no lower outliers, just like we found before. We can do the same process to calculate the upper bound, and we get a value of 133.9 or 133,900. Just like before, that boss's salary is still above that value, so it is an outlier. So by both methods, we can see that the boss's salary is clearly an outlier, meaning that it's unusually high compared to the rest of the salaries at the company. Now we can discuss visualizing these using box plots. So box plots are a great way to visualize a 5-number summary. So basically, a box plot is a visual representation of the 5-number summary. And it would look like this. Okay, note there's two main components. First, there's the box. Coming out of the box are called the whiskers. The box spans the values between the first quartile, in this case 46,000, and the third quartile, 76,000. Has a line at the median, which is the 55,000. The lower whisker goes to the minimum, which is a salary of 38,000. And way over there, we can see a dot at the maximum value, the boss's salary of 164,000. So the box plot gives us more of an appreciate for just how high of an outlier that salary really is. Normally, the upper whisker would go to the maximum. However, if they're outliers, they're represented as dots or asterisks in the box plot. So in this case, the whisker extends to a higher salary, not an outlier, which was 95,000. Same thing would happen if there were lower outliers. One nice aspect of a box plot is that it provides a compact way of seeing your data set divided into quarters, because 25% of data values are below Q1. This means 25% is contained in that space below the box, 25% in the first part, and so on. This also means the box itself, Q1 to Q3, contains the middle 50% of the data values. The space below the upper end of the box is 75%, and you can find all those different other percentages there. Okay, see what this looks like in more detail. We can show the dot plot of the same data set, so we can kind of compare what that looks like. As we can see, the data set has a heavy right skew with 75% of the data values concentrated on the left side of our scale. This creates a long tail of values on the right. So the shape of our box plot with the box on the left side of the scale is an indicator of the overall right skew shape of the distribution. Last section is resistance. So back to our original statement at the beginning of the lesson, the boss of the company whose salaries we've been analyzing is trying to hire you. They say, although new employees start at a salary of 38,000, there is room for improvement. The typical salary is about 65.5 thousand. So recall the mean of the salaries we showed earlier was 65,500 when we had our outlier calculations. This is a measure that the boss is using as the typical salary, and that may seem reasonable, but many people use the average to be typical. Let's look at the typical value, though, or typical salary value. Salary of 65,500 would fall here in the distribution. That means the average salary or typical salary is higher than 10 of the 13 employees, or higher than 77%, more than 3/4 of all the employees. Saying that salary is typical, even though it's higher than the vast majority of salaries, is what we call BS. Bad statistics, of course. Mr. Grass doesn't cuss. In this case, the typical salary might be better represented by the median of 55,000, which falls in the middle of the order of the salary distribution. Let's think about this. Why did this happen? Why did the mean end up so much higher than the median, such that it no longer became a good measure of what is typical? So imagine a year ago, the boss wasn't paid as much as they make now. They made $100,000 rather than $164,000. All right, so a year ago, the mean would have been 60,500, the median of 55,000. Then a year later, they decided to give themselves a big raise, all right, which then gets them to 164,000. All right, that bumps the mean up to 65,500, with the median only going up to 55,000. So with the boss's raise, we can see that the mean change specifically increased by about 5,000. The median didn't change, it stayed at 55,000. Now, we can also look at the measures of spread. We see that the range and standard deviation each grew when the boss gave himself a raise. The IQR did not change. This trait of the median and IQR, where they are not greatly affected by outliers, is called resistance. They're resistant, and that won't change much due to outliers. And in general, when you're working with a data set with outliers or with heavy skew, it's often better to work with median or mean instead of mean, range, or standard deviation. All right, so note, if it's skewed right, you have a right skew, it's going to bring the median or the mean toward that skewness. Same thing if it's left skewed, mean is going to get